theory from the worldsheets. So you heard from Lionel Mason this morning an introduction to Ambitwistor strings, and I will tell you now what that kind of formalism allows you to do at loop level. So this is work with these people: Yvonne Geyer, Lionel Mason, Piotr Turkin. Yvonne was here until this weekend. Piotr is here. He's talking after me. Then Yvonne and I came back to it more recently, also with my student, Ricardo Stark-Muchau. And yeah, hopefully we'll have something soon that I'll mention at the end. Okay, so the idea is that there is a worldsheet model for field theory of massless particles. And whereas in string theory, we have this picture of string perturbation theory as a genus expansion, such that in the field theory limit, we get 3, 1 loop, 2 loops, etc. In these worldsheet models, so in this Ambitwistor string theory, the idea is that this is an equality. And what I will tell you here is about a picture where the loop contributions can be calculated based on nodal Riemann spheres. And we have worked out examples of this up to 2 loops. So this is a node, and you should think about it as the loop momentum flowing through these nodes and introducing 2 extra marked points in a formalism that otherwise is similar to the tree-level formalism. So this is a picture that you would find somewhat natural to find in field theory, and indeed it is what arises. Okay, so here, let me just briefly remind you of the things that Lionel told you. This is the action for the type 2 Ambitwistor string, represents type 2 supergravity. There is a bosonic part of the action that has the structure of the scattering equations, and then there is some worldsheet matter. In this case, we have these 2 fermion systems. You can couple it to worldsheet gravity. In fact, here is already partially gauge fixed by deforming this d-bar operator. It is a Beltrami differential, both E tilde and E. Yeah. Okay. Then the scattering equations are just, well, they will correspond after quantization to this constraint that p squared vanishes, which is enforced by this Lagrange multiplier. And Lionel also told you that P is one form which satisfies an exact equation. So this follows because the action is linear in X. The vertex operators, at least ones for flat backgrounds, only depend on X via the plane wave factors. So you can absorb the plane wave factors into the action. It will still be linear in X. You integrate X out. This is the equation for P. So it tells you that P is meromorphic with poles at the marked points. So there's this delta bar which corresponds to this. Okay? And this is valid then at any genus. And of course, at any genus, this equation for P, at different genus, this equation for P will have different solutions. So the plan for this talk is that first I'll tell you about this, and then I'll tell you about this, and then I'll tell you about this. Because there is no time, I cannot tell you about it, because it's not done. But okay. Yes. Yes. Well, I will answer that question maybe when we reach that stage. So what I will do at level will be for this model. This is like the nice model, let's say. Critical dimension is 10. And we will do some manipulation in this model, and we will arrive at some formalism on the nodal sphere. And once we are there, we realize that actually this is a kind of formula that can be used much more generally in field theory. So then D can be, can be whatever your particular field theory of interest is. So in some sense, this path allowed us to discover a certain formalism, which is then more widely applicable. Okay, so at tree level, we have the sphere with some marked points. I will use sigma for the sphere and Z for homogeneous, just to be clear between the homogeneous surface and the nodal spheres that we will see at loop level. So this is the solution for P. There is no solution to the homogeneous equation because there is no holomorphic differential on the sphere. And so it has simple poles at the marked points with residues corresponding to the momenta. And the sketching equations are that P squared vanishes everywhere. Notice that there are no double poles because the K's are null. So it's obvious then that if the residues at the simple poles vanish, then the P squared vanishes, and these are the residues. They are the sketching equations. So these models were, as Lionel told you, created by Lionel and David Skinner to reproduce the kind of formula that had been discovered by Cachazo and Yuan. And these are formulas for tree-level amplitudes in theories of massless particles, where you integrate over the moduli space of the sphere with n-marked points. There's some integrands, and the measure contains an integration over the marked points, but one which is completely localized by the sketching equations. Okay? So there's some definition of these where only n-3 of these equations are linearly independent, in the same way that after you fix the volume here, only n-3 integrations occur. And here are some examples that Lionel also mentions. So let me talk first about this gravity case. Imagine that you're considering these gravity states. So in general, gravity states with some polarization tensor correspond to graviton, dilaton, and B-field components. If you think about the simplest states, which then can form a basis for the rest, you can have these factorizable states. And then the formula is very simple. You just have one factor that carries information about these epsilons and another one that carries information about these epsilon tildes. So there is this factorization, kind of left-right factorization, although here everything is left moving. And these objects precisely arise from the correlators of the psi and the psi tilde systems. So here is the object, is a Pfaffian of a certain matrix that CHY came up with. This matrix is a 2n by 2n matrix. Lionel told you about it. It depends on the Lorentz invariance, kk, epsilon k. And that matrix is singular on the solution to the sketching equations. So if the sigma satisfy the sketching equations. So to get something that is not zero, you write this Pfaffian where you take 2 rows and 2 columns from the first blocks. And then there is this factor, and this is actually on the solutions to the sketching equations, independent of this choice, and it's also gauge invariant. Okay, so this is a very nice object. And then for Yang-Mills, you take the same object, but then you also have an object expressing the color. This is the so-called Park-Taylor factor. Yeah, this Park-Taylor is a formula for certain four-dimensional amplitudes with a certain helicity configuration, but then people talk about this more generally, to describe these objects where you have this cyclic structure of the marked points, and then to have everything you sum over the non-cyclic permutations. Indeed, for those specific four-dimensional amplitudes, the sketching equation, only one of the solutions to the sketching equations contributes, and these correspond to those spinor brackets that some of you may have seen in these Park-Taylor amplitudes. Okay, so somehow this is, seeing that a similar structure applies much more generally. So this is the tree-level story. Any questions? Good. So let's talk about loop level. So at one loop, we have not only the marked points, but also the modular parameter. So the first question we ask is, what is P? Well, I just erased the equation at P satisfies, but P must satisfy a certain equation, d bar P equals something. But now there's a solution to the homogeneous equation because there's a holomorphic differential on the sphere, and then we just have some constants of integration on the sphere, on the torus, sorry. And then we have the rest, which has, so this will be something with residue 1 at some marked point and residue -1 at some arbitrary point. The whole thing does not have a residue because of momentum conservation at this arbitrary point. So it's just one way of expressing the solution. Okay, so this is P, and then the torus sketching equations say that P squared vanishes. And now this has two types of equations. There's an equation similar to what we had before, saying that the residues at the potential poles vanish. But because of the existence of a holomorphic differential, this does not say yet that P squared vanishes. Okay? There will be some function U of the several moduli, including the loop, well, the loop, I guess I'm already saying what this is, of the L's. Yeah, and you have to say that this vanishes. So this is a different kind of sketching equation that appears at higher genus. And of course there is one here, but say at genus 2, there'll be 3 of them. Yeah. Okay. So Adamo, Casali, and Skinner were the ones who analyzed this higher genus story. And they wrote down a formula for the amplitudes where, well, you have to integrate. So in the path integral over P, it's not completely fixed by that equation that I showed before because there is this zero mode, so you have to integrate over it. And of course, this will be associated to the loop momentum. And then you have something like a CHY integral at genus 1, where that measure will now contain the 2 types of sketching equations. So let's say that these are the sketching equations related to the residues. So you can fix one of the marked points on the torus. And then, yeah, you have the rest of the measure. Okay, so now this is an expression which is derived from the Ambitwistor string, and you can perform some checks on it that make it, show that it's a consistent expression. However, it's not known how to directly evaluate this expression. Still in terms of some theta functions and some objects at genus 1. And then the goal is to try to find something that looks more like field theory, which shouldn't be as complicated as the string theory. And so the basic observation that initiated this line of work was the following. Let's consider this bit here. Yes, that's right. It's some choice of the basis of Beltrami differentials. So this would be a more stringy derivation of something that lie related to Ambitwistor space. No, it's not constrained. Sorry, this is U. I'm sorry, my U's and my M's are indistinguishable. Well, yeah, U will be a function of L, and will be a function of the marked points and of the modular parameter. Okay. Now, it's convenient to write this in terms of the parameter Q instead. And then what you get is something that you can express like this. So I just substituted here the tau with the Q over Q. But I also use the fact that this is like d bar of 1 over U and Stokes' theorem to relate this to a residue integral. And in fact, that's somehow how you should think naturally about this localization on these delta functions. You can think about it as a multidimensional residue integral. So I use this symbol to denote that this is, the contour is around U equals 0. And then, of course, around the other scattering equations, which I'm not writing here because it's not important for these arguments. Okay, so if you have a contour now, what you want to do is apply residue theorem. And of course, you have to check this with the rest of the expression. But what you get is a localization at Q equals 0. And then, yeah, you have some expression like this. So what we did was to turn the torus into a degenerate or nodal torus, which is the same as this nodal sphere. So L will be taken to be the real section. U is a function. Sorry, tau. No. So actually, this is something about this notation. So this is this, but in this mathematical notation that people use in this context, you have this. So actually, you are doing an integration over the. So you either think about it as an integration over, then you would have. So this would be now global differentials, and you would have integration on the entire fundamental domain, or you think about it as a contour integral, and then you think of everything like this, where you'd have, where this is the tau over U. So actually, that's a good point. In the prescription for the path integral, so P will be complex in general. So you have to prescribe that L lies just on a real on a real section. Okay. So L, yeah, is going to become the loop momentum. Oh, yes, but I guess you have to choose a middle dimensional cycle. Yeah, but it has to be a sensible cycle. And that cycle, if you do a model transformation, actually, it will change that cycle. But one good cycle is the real cycle, and then all the other ones related by model transformations. Okay, so now, what is P at q equals 0? That holomorphic differential will no longer be holomorphic, because there is no such thing on the sphere. Instead, it will have poles at the marked points. So these are the marked points at the two ends of the nodes. And then you have the rest as you have at tree level. So now it looks very similar to tree level, with some particle with L and some other particle with minus L. The scattering equations are not now that p squared vanishes, because we dropped the u equals 0 equation. Instead, it's this that vanishes. Okay? Because L is not null, so actually this is the object which has only simple poles. Otherwise, you'll have double poles at these points. And then, yeah, again, as at tree level, because that's what this looks like now, the statement is that the residues of these at all the marked points vanish. And what does the formula for the amplitude look like? Well, it has this loop integration, but there's a 1 over L squared appearing. Actually, it comes from this u at q equals 0. And then you have an integral over the moduli space of the sphere with n plus 2 marked points. But the scattering equations will be different. That's why I put this superscript 1. And there will be some integrand. So this looks very much like a tree-level CHY formula. These integrands, well, you can just take what was on the torus and take the limit when q goes to 0. This is not necessarily a trivial limit, but this is it gives you the correct results. And this formula is now part of a d-dimensional formalism. So this was done in this theory, which has a certain critical dimension that is important for modeling invariance. And modeling invariance was actually crucial in this argument, because it meant that the boundaries of the fundamental domain, the only boundary that contributed was q equals 0. Sorry, it meant that actually the others were not boundaries because they are identified by model transformations. However, once you arrive at this, then you can ask yourself, if I take some other field theory for which I don't know the Ambitwistor string model, or maybe I can sort of guess some things, can I write amplitudes? Yes. Okay? And in fact, this is precisely what we did, because we also got expressions for Yang-Mills theory and for gravity also without supersymmetry. Okay, excuse me? Yeah. No, I'm saying that if I'm in the wrong dimension, the expression on a torus does not make sense. Because to be defined on a torus, you need modular invariance. Because it must be invariant for a modular transformation. Once you get here, there is no modular invariance anymore. Yes?
Another thing you can do to really stay clean is to compactify your theory and to send the mass of the Zeta state to easy. So in the non-compact direction, you have just this D element, but it's equivalent to it gives the same moment.
Okay, for gravity and Yang-Mills theory, you actually get the same kind now of formula. So this K is again some kinematics-related object carrying the epsilon. This some color-related objects. There's some natural extension of this. In the supersymmetric case, the objects that you would get, say, from the type 2 case, you have a sum over spin structures at genus 1, and then you take, so some will correspond to Ramon running in a loop, some will correspond to NS running in a loop. You take the limit when Q goes to 0. Some of these two are actually blowing up, but in such a way that the limit is finite, because the divergence cancels between the two. In the non-SUSY case, so the color object will be the same in Yang-Mills. The K object would just be the NS part. In fact, you can also write some sort of half maximal supersymmetry by putting one SUSY and one non-SUSY. Yes? Yeah, that's right. But, well, this one is the only one where you can find the pole. So the other ones would correspond to some, to something that is not contributing here. I mean, you have to, what is here, you have to check about potential. Yes, yeah, that's right. This is true for one loop, okay? Well, at higher loop, so we'll see at 2 loops. If you're careful, you only have one contributing. But that requires you to make special choices, which somehow make sense from the field theory point of view. Okay, let me just say that this NS part can actually be thought in some way. So I've told you about this Pfaffian, the CHY Pfaffian at 3 level. Here, you can actually consider a Pfaffian with 2 more particles, with some states, and you can, you can associate a sum over these states and define it in some way using a completeness relation, such that, these formulas are equivalents on the scattering equations. So the formula that you naturally get from the super Ambitwistor string, you take the NS part, it gives something which is equivalent to this one. But somehow these equivalences may depend on the use of the scattering equations, because anyway, this is all defined up to, up to the solutions to the scattering equations. And actually, David Skinner and his student Kai Rohrig had a nice paper formalizing this by essentially saying that the node can be thought of as an operator in the cohomology of an appropriately defined BRST operator. Okay.
Why is it important to include the worldsheet fermions to get the
That's that's a good question. I guess it's related to the fact that the bosonic Ambitwistor string is this weird theory. Somehow, you know, it's not just a trivial limit of string theory when alpha prime goes to 0, and this type 2 theory is well defined, and so you can use it and just sort of truncate it. But you know, there is no Ambitwistor string for this that gives you this result only. There is an Ambitwistor string for type 2, and then you look at it and you sort of, you do things that people have actually done similar things in string theory, right? You know, recognizing which bits correspond to certain states running in the loop. So the vertex operators for the states which have these epsilons. So this case arise from the correlators of these fermions. Yeah. Excuse me. So there is no non-supersymmetric Ambitwistor string theory. There is only a non-supersymmetric formula for the amplitude. An amplitude of pure Yang-Mills theory, in this case. Pure Yang-Mills theory, gluons. Gluons, and here gluons, gravitons, here gravitons, dilitons, and B field. So an SNS gravity. Yeah, I mean, the theory of these states. So one polarization comes from here, the right polarization comes from here. Well, in this case, yes. So in this case, there's a derivation from the string, but let's say, you know, I'm some sort of amplitudes guy and I want some formula for amplitudes that looks quite different, and this is it. Okay? Sorry? Well, it's, you mean of this theory or of this theory? Yes. Well, you know, I don't know what's the Never-Schweitz. Well, the only way they have to define a Never-Schweitz theory here, it's not somehow, you know, it's just at the level of these amplitudes. I don't know of a theory that is just these states. Well, the only thing I know is that if I look at the amplitudes and their factorization, I can look at, say, the poles of the loop integrand and check that this formula only carries the degrees of freedom of the non-supersymmetric theory. But I don't know exactly, yeah. You know, the full supersymmetric, so yeah, this is the GSO projection, is the full sum over spin structures. And then when I start breaking it, I actually don't know. Yeah. Yeah. Yes. Are those also removed somehow by these formulas? So there is no, you know, these formulas for, in the case of n equals 4, say, at one loop, I guess that there have been some proposals, but they've not been very well studied. But if you're starting from 10 dimension and reducing, the spheres is already included. Oh, yes, yes. Oh, yes. That's right. You have to remove them by hand when you do pure Yang-Mills? When I do pure Yang-Mills. So the pure Yang-Mills, so pure Yang-Mills will be just the NS part. This NS part has two contributions. One of it corresponds to a vector, and then if you dimensionally reduce, then somehow you're taking part of that vector to become scalars. And they are there. Yeah. So well, if you do the, sorry, the Yang-Mills amplitude in 4 dimensions. Oh, yes, sorry, because this object, when I say this object has two contributions. There's a contribution where you get some sort of, some Pfaffian, some contribution Q to the 0, and some other contribution where you take the coefficient in the Taylor expansion Q to the 1/2, and then there's a D minus 2 here. And in fact, to get the NS part, you must also adjust this D. So this D minus 2 would be 8 from 10 dimensions, but if I just want pure Yang-Mills in 4 dimensions, then I would also have to adjust this to be 4. And in that way, I would be throwing away those scalars. Okay? Well, so I will just very briefly say something about two loops. So there was a work actually based on the pure spinner Ambitwistor string by Casali and by Adamo and Casali, where you obtain a formula 4 points, and then we went on to work out how that looks like in the binodal sphere. And more recently, then Yvonne and I went to look at the n-point formula from the RNS Ambitwistor string, to try to understand some more general features. So the idea here is that you apply the residue theorem twice. And this step is easy. This step is not easy. Somehow, the fact that this localizes only here is due to some special choices that one makes about the scattering equations. What it tells us, so let me just go here and tell you what the scattering equations look like. So there is some P. That P is very much like the one that I wrote there, except that now there are two terms like the first one. There's one for L1 and another for L2. There'll be, there are two nodes, so there's an omega 1 plus 1 minus and an omega 2 plus 2 minus. So that's fine. And then you want to know what the scattering equations are. So you do something similar, but then there is an issue, which is the following. If you want this to be the scattering equations, this will not give you. So okay, in the first approach we had to the problem, we didn't do this derivation rigorously. We just sort of tried to guess the final answer. And although this seems like something reasonable to write, this is not the correct answer. Notice that you could also have added here this. So the scattering equations would be that this vanishes. You could have that. There are no double poles in it. It could be there. And in fact, it must be there. And it must come with a certain coefficient, which is only fixed up to some sign. And the reason for that, from the field theory point of view, is that in the loop integrands, you need certain type of propagators. And for those propagators to be able to form, you would need this. Okay? Weirdly, though, it doesn't completely fix this. So you could choose the scattering equations with the plus sign and with the minus sign. And in the supersymmetric case, you can choose either of them. So here, when you are going on to this stage, you have to make some choices about the scattering equations, the scattering equation that you want to exchange for the generation in this residue theorem. And if you make a smart choice, then you'll land here, but you could make either of these two choices. So maybe I should just, okay. In the supersymmetric theory, that's fine. If you want then formulas in the non-supersymmetric case, actually you need contributions from both. You have to somehow take an average of the two types, essentially because in terms of diagrams in the loop integrand, in terms of trivalent diagrams, it's like the SUSY theory cares only about diagrams like this, but the non-supersymmetric theory cares also about diagrams like this. And somehow, yeah, that is an important subtlety which makes the non-supersymmetric amplitudes start looking significantly more involved than the supersymmetric ones. So this is something that we are that is now in progress. Apart from these subtleties, it looks similar to the one loop case, and I think I should end here. Thank you. Excuse me? If I don't have it? You mean, so if I start, let's say, at one loop, right? And I say, I don't have modeling invariance, then I don't know, the formula is not defined on the torus over the whole thing. Yeah, well, in order to make this argument that I told you work about these residue arguments, I need the modeling invariance, because that provides, that makes that leads to the fact that it localizes only at q equals 0, because there will be no other possible. Yeah, exactly. That's right. Yeah, so actually what we're doing now is we went to G equals 2, and in the supersymmetric case, we wanted to understand what happens in the non-supersymmetric case. Probably 2 loop will be the last time we do that. And then, yeah, we would like to know how it works at higher genus. Because, well, this looks like, yeah, it looks like a nice toy model for string theory. There's this nodal expansion. There are certain features of the formulas at 2 loops that remember a little bit that they come, and they would have to be like that anyway, even if we didn't start at higher genus. They are just features of the field theory formulas in this type of expression that have the counterpart in the higher genus formula. So if we can work at the level of the nodal sphere and write some expressions, maybe for a 4-point amplitude, I don't know if you could try to guess what this lifts to at higher genus.
The point is that the moduli space also at 2 loops is always of a marked sphere. The moduli space of integration.
Yeah. So well, it. So this is genus 2 Riemann surface. After this is the sphere moduli space. 4 marked points. So actually, so you start with 3 modular parameters at genus 2. You use 2 of them to do this degeneration. You're left with 1, and that leftover one will be a cross ratio of these marked points, of these loop insertions. Yeah, no, you only have massless states running. Yeah.
It is more or less what you can expect in string theory, because in string theory, when you have only massless states running in the loops, you can think just a pinch in.
Yeah.
Not a pinch in, yes, a very long.
So actually, part of these stories were actually inspired by old work in string theory. I was actually discussing that with Paolo recently on these gluing operators. Yeah, I mean there is certainly some connection here. I guess at this level, this is already field theory from the start. So somehow you just land on these things in a derivation. I mean, yeah.
Okay, so maybe we continue with the
Sure. Yeah. Thank you.